This is the Python code given by the authors of the book that I use. It is the one of the Python implementation. The author used the priority queue. We learn about the priority queue, and then based on this priority queue, we can find the shortest path. So the shortest path means we want to find for every possible of vertex. When we have the every vertex, so P is for every vertex, and then V is in the source. Source means the node that you have in the graph. If it is not in the source, then the information will be infinite. It means we cannot reach that node. But if it is in the source, then we will make it as 0. So the priority queue will always keep the information about the vertex. And then whenever the priority queue is not empty, then we will do this part. Whenever we find the minimum, we will use the minimum among the possible distance from one source to another destination, and we put it into the key and U. So the cloud will be updated, and we will delete the PQ locator. The PQ locator is just to put the priority queue. And for every of the incident edges, this is the incident edges of the vertex U, we want to find the opposite. And we do the checking like what we learned about the edge relaxation. So in the edge relaxation, we want to check whether the edge is less than the dz. So we want to find this one, whether the dz, which is the current distance from the origin, will be smaller from du plus weight e. So the formula is when we use the shortest path, we can have this pseudocode. So we can apply this one into the code in the Python implementation. It means, in the upper part, you can apply any kind of algorithm. In the book, they try to adopt the priority queue. So this section has been adopted from the priority queue, and this one is the edge relaxation. Why Dijkstra algorithm works? Dijkstra algorithm is based on the greedy method. Greedy. Greedy means I want to check all possibility. So I will check A to B, A to C, A to D, B to C, B to E, E to C, and all possibility. And then again check another possibility if there is any update. It adds vertices by increasing distance. Suppose it didn't find all shortest distances. So let, for example, F be the first wrong vertex the algorithm process. When the previous node, D here, on the true shortest path was considered, its distance was correct. So if you know, before we find the F, we will check the AD, and then we will check ACD. Okay. And we know that, okay, it is correct that the ACD has distance 3. AD has distance 4. AD has distance 4. ACD has distance 3. Okay, because 2 plus 1. So it is correct. If we consider this one, 2 plus 9, 11, okay, and then we have 2 plus 1 plus 5, yeah, it is 8. So we can say that, yeah, this is the relaxed part because we are sure that this is the shortest. So by adding this one, there is a possibility that this is another shortest instead of ACF. Thus, so long as DF is greater than DD, distance to F is greater than the distance to D, F distance cannot be wrong. So if this one is 3, and then this distance is 8, then no problem. This is correct. There will be no wrong vertex. The issue will be if there is a negative weight edges. What is negative weight? The negative weight means if you find like this one, it is -8. If a node with a negative incident edge were to be added late to the cloud, it could mess up distances for vertices already in the cloud. The Dijkstra algorithm is based on the greedy method. It adds vertices by increasing distance. So it will increase and increase whenever we move to the next node. C is true distance. C true distance is 1. Okay. But it is already in the cloud with the D distance C equals to 5. So if you can check this one, A to C, it is 6. Okay. And then what about the other node? Okay, we can go to D. A to D is 4. Okay. C to D is 1. Okay. And if you check this one, okay, I can go from A to D, and then D to F, and then F to C. Why? Because it is the shortest one. 4 plus 5, it is 9. 9 minus 8, then it will be 1. However, if you trace back, when you check this one, when you try to find from A, you will check A to B, A to C, A to D. And then you will have the A to C is 6. At the first time, A to C is 6. But we know that A to D is 4, and 4 plus 1 is 5. So we can update C equals to 5 because 5 is smaller than 6. And then because it is 5, of course, we will put this one into the cloud. Once we put this into the cloud, we assume that it is visited. If it is visited, then we cannot revisit. If we cannot revisit, actually, we can get the new shortest one, which is 1. Because if we go to A, D, F, C, the distance will be 1. But Dijkstra algorithm cannot work with this one. So this one we want to learn that Dijkstra algorithm does not work for the negative with edges. That will be one of the issue for the Dijkstra algorithm. And there is another algorithm that can work for the negative width. We call it the Bellman-Ford algorithm. The Bellman-Ford algorithm works even with negative width edges. And the Bellman-Ford algorithm, it must assume directed edges. You know, directed edges. So in the directed graph, we have direction. So directed edges means we have this as the directed graph. For otherwise, we will have negative width cycles. Iteration I finds all shortest paths that use I edges. Yeah, of course, this kind of mechanism, we will check from every vertex and then for every edges, and the running time will be something like this one, O n multiplied by m. Can be extended to detect a negative width cycle if it exists. So first, let's see. This is the algorithm of Bellman-Ford. We have G, this is the graph, and S is the starting point. We want to find all the vertices. And if the V equals to S, then let's set the distance equal to 0. If the distance, if not S, then let's put the V as infinite. So we will check for every of the node from 1 until n minus 1. And then we want to check for every of the possible edges. Let U be the origin of the edge E, and then let Z be the opposite of U, comma E, and then R will be the distance U plus the width. If R is less than the get distance, then let's set the new distance. Let's see with example. So at the first, we want to set A equals to 0, and then all other nodes are infinite. B, C, D, E, F, they are infinite. So we start with A equals to 0. And then next, we will check the edges from A. So we want to check from A to B, from A to C, and from A to D. Here we know that from A to B is 8. So we update this one, 8. And then we have C is minus 2. So we put minus 2. And then we have D equals to 4. So we update with 4. From this, we know that the minimum is C. We will get this one. We will start with C and then check all the possible edges. So this one we'll check from C to B. Minus 2 plus 7. Now it will be updated to 5. And then minus 2 plus 1. It will be updated to minus 1. Minus 2. There is no direction to here. Okay. Then we will not calculate this one, but we will calculate from C to D, which is minus 1, and then D to F. Minus 1. Oh, this one is 9 because we assume at the first we have the 4 plus 5. Okay. So we are not updating this one first. We have the assumption that A and D, we have the distance 4, and then the F is from D, A, D, D, F, then it will be 4 plus 5. Then we update with 9. What about this E? We have E at the first, we have minus 2, and then we update it here 7, 5, 5, and plus minus 2, we have 3. However, if you check from A to B and then B to E, actually we have 6. So the origin one, we are starting from A, and then if we go to E directly from A to B to E, then it will be 6. However, there is an option that we can go to E through A, C, B, E, which is 3, and we can have another option from A, C, and E, which become 1. So from this one, we put all the distance again. Now B equals to 5, C is still minus 2, and D has been updated into minus 1, E has been updated to 1, and F, it is still 9. The next minimum is 1, so we will go to the next. Now we are going to update the D. D is minus 1, and if we go to F, then it will be minus 1 plus 5, and it becomes 4. So we need to check other possible whether there is a new possible route to minimize the distance or not. And if we check this one, A to B, sorry, this one. So A to B can go from C because we can get the minimum, and then A to D we can go through C, and then if we want to go to F we can go to A, C, D, F, and then if we want to go to E we can go to A, C, E. So the F will be the next, and we can get the result based on this one. So this is the final result with the Bellman-Ford. All the distance will be noted, and this is the shortest distance from A to other node, which is B, C, D, E, and F. There is another algorithm. This is not in the book, but I would like to explain to you. So if you can use this as well, it is also good. DAG-based algorithm. DAG means the directed acyclic graph. Works even with the negative weight edges. The DAG you already learned from the previous one. This is the directed acyclic graph. It means there is no cycle. It works with the negative weight edges, and then it uses topological order. Do you know what is topological order? In the previous one, we use the minimum one, And then whenever we want to check the distance, yeah, we do not know which one is the first. If I have the A and then B and A to C, A to D. So if you are using the dictionary, there is no sequence, there is no order. In this algorithm, they will put one step here. It is called by topological sort. So I would like to sort the vertices based on the order. Let's say I have the A, okay, and then I can go to B, I can go to C, I can go to D. In the previous algorithm, in the Bellman-Ford algorithm, you can check if you want to go to D first, and then you can go to B, and then you can go to C. It is fine. But in this DAG, we want to sort A, and then we go to B first, and then go to C, and then go to D, because we want to sort it. Sort based on the topological. The topological means, yeah, if you have a string A, B, C, D, of course, it is the sequence A, B, and C, and D. So if you have like B, and then E, and then H, and then G, then the sequence will be B first, and then E, and then G, and then H. So we are making this order, and this order will be used for the for loop. That's the only difference. It doesn't use any fancy data structure. And based on this one, we can see it is faster than the Dijkstra algorithm, and it can be used for the negative weight edges. So the running time, yeah, we can have the maximum running time is O(n plus m), okay, because this will have m edges. So for every vertex, we will have the maximum f is m edges, then it will be n plus m. So the idea is almost the same with the Bellman-Ford. We will put all the nodes as infinite, and A, let's say A is the starting point, then A will be 0, and the remaining will be infinite. And then we will check. Let's now, with this information, B, it becomes -2, and then C, it becomes 8, and then D, it becomes 4. So we want to check based on the topological order. So we will check based on the B first, okay, and then B, we will check for every of the possible. B is going to C. So we have updated the -2 plus 7, and it becomes 5. And then -2 plus 3, it becomes 1. And then to D, it is -2 plus 1, it becomes -1. Okay. And then, yeah, let's say this one, we have another, this is a direction from B to E. So -2 plus 9, it becomes 7. So we updated the distance for each vertex. And then we want to continue because we already finished with B. We continue with C. And then again, we continue with the next topological order, which is D. Okay. If we go to F from C, then -2 plus 7, it is 5. And then we have 5, -5, then it becomes 0. For the route from A to E, originally it is 7, but if we go from B to D, it becomes -1, and -1, if we go to E, -1 will be added by 5, then it becomes 4. Okay, that's the Bellman-Ford and the DAG examples. I hope that you understand the mechanism. So what I want to explain next is about the directed graph. When we learn about the graph in Dijkstra algorithm, we can use the undirected graph, but with the Bellman-Ford and the DAG-based algorithm, we assume that the graph is a directed graph. I think I will just have time to explain the concept of digraph, and yeah, let's see until which section that I can finish this part. Directed graph or digraph. Many literatures says directed graph as digraph. So a digraph is a graph whose edges are all directed. It is a sort of directed graph. A directed graph means there is a direction like this one. So the application, for example, if you are driving, you know, a one-way street. And then we know flight is one way. And if you go back to the origin, it is two ways. But a flight will always have one direction first. Task scheduling. So in the manufacturing or in the industry or in the transportation, you will have one origin and one destination. So when we deal with the digraph, there is also a property. A graph G, we have V, which is a set of vertices, and then we have E, which is a set of edges, such that each edge goes in one direction. So this means that it's at A, B, at A, B, it goes from A to B, but not B to A. If G is simple, simple means every graph will have only one particular edges like this one. So M is the number of edges, is less than equal to n multiplied by n minus 1. If you still remember the graph properties, okay, in the graph properties, yeah, we also make the number of edges according to the number of vertices. Okay. So this is the properties for the directed graph. If we keep in edges and out edges in separate adjacent series, we can perform listing of incoming edges and outgoing edges in time proportional to their size. So when we learn about the graph example in the Python, we have the incoming edges. You can see what are the incoming, and you can see also what are the outgoing. So that's we call it the in edges and also the out edges, and we can show what are the vertex. In some application like scheduling, at A, B, it means that the task must be task A must be completed before B can be started. So maybe this is an example about a route, okay, or this is like the course, the course completion. In our department, we don't have a kind of sequence, okay? But in some other university, they have a sequence. Let's say you complete the calculus 1. And then if you do not complete the calculus 1, you cannot take the calculus 2. Okay? So in this case, it's almost similar. Okay? We have, in our department, we have computer programming, we have the data structure, but we don't have any mandatory. Let's say if you don't take the computer programming, you cannot take the data structure. We don't have that kind of mandatory. But of course, if you take the computer programming, yeah, it will be good for the data structure. So that kind of things we can show it in the directed graph. Okay. Okay, I think I will stop. I will continue this explanation on Friday. So please go to the e-class and you can check the review quiz in next 1 minute.